We're starting to build on top of it, so I'll give a nice update on that as well. And so field optimization is essentially a gradient-based, multi-objective, multi-variable optimization process where you can tie different objectives and constraints to different design parameters of the implicit directly. And it removes the need from having to mesh complex structures like these lattices because all of the optimization happens on different fields of background grids. And so it's built on top of a very modular architecture in nTop, where you could set your objectives up front in nTop, like traditional topology optimization objectives, and you can drive different parameterizations that you've created. So you could use nTop to do a design study to calculate the effective material properties of a lattice component, like we saw with Lattice Robot, which is awesome. I'm super excited for Lattice Robot to feed in their stuff to our field optimization. That gets compiled into what we call a material model, which then gets packaged as a block in nTop that can be used in traditional optimization processes. So what does this really look like? OK, so a geometry parameterization. Here you have some parameters of points in space, a parameter for cell size, a parameter for beam thickness. And we can measure then what happens when you change those beam thicknesses and point sizes from a material standpoint. You essentially create stiffer or less stiff or directionally adjusted materials. That material model could then be used to optimize a medical implant, where you maintain a certain porosity, but you target specific stiffness parameters. And you can see there's two fields in the background that the optimization is run on, one for the relative density, one for the cell size. Key result here is 15% mass reduction from one of our customers who makes these hip stems, and you have tailored material properties, so you get the flexibility that you want. Another parameterization that you can create with an implicit model, because remember, the geometric operations they kind of happen for free. So you can do these shelling operations where you just add some wall thickness, you fill the part with some type of lattice, and again, you want to create certain material properties. You want to create stiffer parts. You want to create anti-buckling parts. And so this was used on the NASA Excite bracket. And the goal here is essentially make the lightest weight bracket that is subject to buckling and stiffness constraints. So you basically want to raise the minimum modal frequency of the part. And so compared to a traditional topology optimization, what does this look like? You could see the traditional top-op part has kind of these thin, wiry members at the top connection that probably would buckle at some point. The field optimization, because it knows it's creating a new material that's a shelled and infilled part, actually creates a kind of more inflated overall global result. But then there's a secondary set of optimizations that happen to control the wall thickness, the orientation, et cetera, of the infill. And so what you get is a part that has 81% increase of minimum modal frequency, much higher buckling load factor. Max displacement is still within the proper range, and actually the part comes in even lighter weight, 19% on that. And so when you look at these type of lattice structures, a lot of times they don't increase the stiffness of a part, but they could be used to increase the strength by reducing the buckling of by reducing the propensity for buckling. And so field optimization ultimately it's this modular framework. And so I'm super excited about the different types of new problems that it opens up, from periodic lattices. One I'm most excited about is building in traditional manufacturing constraints. So this is a field optimization that's targeting a structure for a machined grid stiffened panel. We can do traditional shape optimization as well, and as well as composites, so figuring out the orientation of composites in a 3D space. So in conclusion, at nTop, as manufacturing continues to advance, it's my belief that software should be pulling us forward and not holding us back. And so with that, there's a number of different applications. I showed a couple that were through here. Definitely later today, Husman's talk at 2:20. Francesco Leonardi is also speaking at 3:15, I believe, on the other side from Punto Zero, some of the most exciting work in nTop as well, and then there's a computational design panel a little bit later today. So with that, thank you, and great to see everybody here.